The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
And I thought that what we do today is first go over this syllabus for audition, which is the second part of the course, just so you get an idea of what's in store for you. And then today's lecture will have a big part on sounds, which have physical properties that are very different than the light stimulus you guys have been talking about so far in the course. And we're going to illustrate different types of sounds, very simple sounds like pure tones, and very complex sounds like human speech, which have many, many components in them. And then we'll get into the auditory system, first starting with the auditory periphery. And we'll talk about the three basic divisions of the auditory periphery, which are the outer, middle, and inner ear. And today we're really only going to have a chance to focus on the functions of the outer and the middle ears. And so we'll talk about the function of those structures. So as far as the syllabus goes, each of the lectures has a title. So today's title, October 28th, is Sound, External, Middle, and Inner Ears. And each of the lectures has a reading or more accompanying it. And so most of the readings are from the textbook. So there's a textbook, Schnupp, Nelken, and King, which is a very good, up-to-date textbook written by two psychophysicists and one physiologist, Israel Nelken. And it's written at just the right level for this class. That is an advanced undergraduate textbook. So it's pretty easy to read, or it should be very easy to read, and it's written very well. These guys are good writers. They have many examples of auditory demonstrations that you can listen to. Just by clicking in the margin of the text, the demonstration will come up. And as you can see, after today's lectures, I like to give demonstrations because I like to listen to what we're talking about in terms of how does it really sound to you as a listener. So I'd encourage you to get that textbook. Now you can buy a hard copy, or if I'm not mistaken, Michelle, you can get a free copy online, is that right?
There's an online version as well that you can read on the web.
Okay, great. So, if you have any trouble figuring that out, let me know. But I think you should easily be able to find the online version. And it should have the demonstrations that you can listen to with earbuds or headphones. There is for today, so these passages from the textbook. And then for today and for many of the lectures, there's another reading, which is a research paper. This one is by Hoffman, Van Ryswyk, and Opstal, and it's titled Relearning Sound Localization with New Ears. And this we'll talk about in class right at the end of today's lecture when we talk about the function of the outer ear, or the pinna, so-called. And they did a very interesting experiment that addresses what is the function of your external ear. So people always ask me, what am I responsible for in these readings? Well, this is a very specific paper. It has a lot of interesting research methods. The subjects were human volunteers. And there are a lot of details in there that are not that important. What I'm really focused on having you learn is the take-home message. And the take-home message from this paper is, what is the function of the outer ear? And what is this twist in the title? How can you relearn sound localization with different outer ears? We'll talk about it in class. But I want you to get the take-home message from these research studies, because they're sort of what we do as professionals in the auditory system. Our day-to-day living is doing research, in some cases on human subjects, in some cases on individual molecules. But how can we learn about hearing from doing these research studies? And I have picked good papers, good research studies, because they really tell us something. There's plenty of stuff out there that gives sort of equivocal results. But this is a really good paper, and you have a take-home point from it about how you use your outer ears to localize sounds. So that's an example of a research paper that goes along with this lecture. So just coursing through the syllabus, on Wednesday we'll have a lecture on hair cells. Next week, we'll talk about the auditory nerve, which is the nerve that sends hearing information from your ear into your brain. And we'll talk about frequency resolution, how we can tell one frequency from another. At the end of next week, we'll be talking about the brain, the cochlear nucleus, and all the interesting unit and cell types in the cochlear nucleus. The following week, we're going to be talking about hearing loss, how there can be problems with your hearing. Many of them are treated at the hospital where I do my research, which is Massachusetts Eye and Ear Infirmary across the river. And there, when the surgeons in my department encounter a deaf person, they give them the option to get a cochlear implant. So a cochlear implant is a device that can be put in your inner ear, and it can restore your sense of hearing. And we'll have a demonstration by a cochlear implant user who comes to class on that date and gives a demonstration of her cochlear implant, which has restored hearing to her, although not perfectly. So then later on in the semester, we'll talk about various other topics on up through the auditory cortex. And finally, we are going to have a tour of the Hearing Research Laboratory at the Massachusetts Eye and Ear Infirmary, where we'll meet over there and we'll encounter various research projects that are currently going on, and we'll talk about them. There is a written assignment. I guess you guys had an assignment for vision in the class, right? A written paper. Okay, so we have an analog here in the auditory system. And this is the assignment. You can read it later at your leisure. It won't make much sense right now because we haven't talked about neural circuits for localization of sounds yet. You can look on the syllabus. That's about halfway through the second part of the class. And there's a lot of details here, and it asks you what's updated since an original model was postulated by a researcher called Jeffress. Okay, so that's a paper. I don't think I said how long it should be. How long was the paper for vision? Was there a length? 4 to 6 pages? Okay, 4 pages sounds good. If you really want to write 6, you probably could. But we'll talk about this when we talk about sound localization in the class. And I think the due date here is written. It's the date of the lab tour. And then we have a final exam in the class. And I think as Dr. Schiller talked about it the very first day, the final exam will be weighted toward the auditory system, which we haven't had a test on by the time this exam rolls around. So I think it's going to be 2/3 audition on the final exam and 1/3 vision. And there are several review sessions for both senses planned at the end of the semester. Okay, so any questions about the organization of what we're going to do? Okay, so I'll start today's lecture. And I think the PowerPoint files for today's lecture and all the rest of the lectures for the rest of the semester are available on the course website. So you can look at them now or as the lecture comes up. Okay, so first we're going to talk about the physical characteristics of sound. which is very, very different than the characteristics of the light stimulus. And maybe light stimuli are so obvious that Peter Schiller probably didn't spend much time in his lecture about it. But I'm going to spend 10 or 15 minutes here on the physical characteristics of sound, because it's very different than the light stimulus. So sound is a mechanical radiated energy transmitted by longitudinal vibrations of a medium. So you have to have a medium to transmit sound. You can have light go through outer space in a complete vacuum, but in outer space you can't have sound because you have to have a medium. The medium can be various types of things. We're going to talk mostly about sound in air, but you could have sound in water, right? Whales make songs and they sing to each other. One whale listens to another, and in between the two is the medium of water. You can have sound in a solid, right? If you live in an apartment room and you hear your neighbor's music, you especially hear the bass because that low frequency sound transmits pretty well through solids, like the solid of the wall in between the two apartments. Okay, sound can go in many, many different types of media. In air, like we're going to use mostly for this course, you can think of sound as being produced by a sound source, like the piston of your loudspeaker. And the piston goes back and forth, is driven back and forth by an electric voltage. And when it goes this way, it presses on the air molecules in front of it. And it presses them so they're closer together and makes them a little bit higher in pressure. And that's what's meant by this compression or condensation. And these dots close together means a little bit of an area of high pressure. Then as the piston moves the other direction, it rarefies the air. It drags some of the air with it. And so that little space right in front of the piston has a lower pressure because there are fewer molecules per volume than before. So this energy then is transmitted through the medium to whatever, a microphone which can detect sound, or a listener which can listen to the sound. If you have a microphone or some kind of detector that can plot that pressure at any one point, let's say the microphone is right at the edge of this paper, and you graph the pressure as a function of time on this graph. So here's pressure, and here's time. As those radiated energy wavefronts pass you, the pressure will go up, and then it will go down, and then it will go up and go down. And it will repeat over and over as long as that piston moves. So this horizontal line is simply the barometric or static pressure of the air. And sure, the barometric pressure changes a little bit. If there's a hurricane coming, it gets way low. And if there's a high pressure like we have right now, sunny climate, the barometric pressure goes up. But those are very slow fluctuations. And this sound waveform is a very, very fast waveform that goes many times per second. In fact, what we call as sound frequency is the number of oscillations of that pressure wave per second. And they are very fast. As you can see down here on this so-called audiogram or frequency curve for human hearing, the frequencies, which are on the x-axis here, go from 10 hertz. Hertz means cycles per second. So 1 hertz is 1 cycle per second. And that is a frequency that's so low it didn't get on this graph, because humans aren't sensitive to frequencies that slow or that low. Usually the lower limit for human hearing is considered to be about 10 cycles per second, or 10 hertz, and it extends all the way up to 20,000 cycles per second. And in the middle of the human range, we'll be talking about hearing a lot at a middle frequency of about 1,000 hertz. So that's a nice round middle frequency for you to remember for human hearing. So we're talking about pressure oscillations in terms of thousands of times per second, or hundreds of times per second. So they're very fast. There will be examples during our course where the auditory system, the auditory neurons, keep track of those cycles, even though they're going back and forth thousands of times per second. Okay, so we'll come back to that in future lectures. Now, this is the audiogram for human hearing in the solid curve here. This is supposed to say human if you could read it. And on the y-axis is how strong the stimulus is, how loud it is, or in terms of physical characteristics, what the sound pressure is. Okay, and this scale goes from -20 to 140, and the units are dB SPL, and that stands for decibels sound pressure level. And whenever you hear level in a formula, you should perk up your ears and say, ah, that means there's a logarithm in the formula. And sure enough, the formula for sound pressure level is 20 times the log of whatever sound pressure you're talking about, whatever you were listening to or measured by your microphone, divided by some reference pressure. That's the formula. And the reference pressure is given as 20 micronewtons per square meter. Okay, so let's figure that out. What is newton a unit of? Anybody? Right, force. And meter squared is area. So we're talking about force per area. And that's pressure, right? So Newton obviously was like Hertz, one of the people who was interested in physics. And Newton is a unit of force per square meter is pressure. Now, in more modern terms, the unit micronewton per square meter has been renamed to be a Pascal. Okay, so abbreviated PA. Okay, so it's the same. 1 Pascal is 1 Newton per square meter. Okay, and in this case, we're talking about micro. Newtons are micropascals. So why is that number chosen as the reference for this very important sound pressure level scale? Well, it's actually chosen with the hearing system in mind. What they did in the 1930s when this was being developed is they rounded up a bunch of people at a county fair, gave them headphones, and they said, we're going to try a nice mid-frequency. Let's try 1,000 hertz. They gave them a tone at 1,000 hertz, and the listeners listened to it, and they said, I can hear that fine. Then they turned the level down a little bit, and the person says, yeah, I can still hear that. Then they turned it down so much that the person didn't say, I hear something. They were silent, okay? They turned it up a little. Said, yeah, I hear it. They turned it down. They titrated the levels until it was right at threshold, just barely detectable. And they took an average of 30-some people, and they said, that is going to be the basis of our sound pressure level scale. So it's actually a term that was derived biologically by testing people's hearing. Okay, so if that's kind of a nice story. I wonder if it's true. Well, let's look at it. Where does the human hearing curve at 1,000 hertz fall? Well, where should it fall if 20 micronewtons per square meter is the pressure you're talking about? It's the same as the reference pressure. What's 20 over 20? It's 1. What's the log of 1? 0, correct. 20 times the log of 1 is 0. Sound pressure level 0. We'll look on our curve right here at 1,000 hertz. It's pretty close to 0. Why might it not be exactly 0? Well, the people that were used for this curve are a little bit different than the ones in the county fair. We'll study later on that some people have a hearing loss. Hearing can be affected by the room that you use. Maybe there was a lot of yelling and screaming at the county fair. We have better rooms to test hearing now. It turns out that the human hearing curve is actually a little more sensitive at 2,000, 3,000, and maybe 4,000. So when the pressures go below the reference pressure, the number becomes less than 1, and the logarithm becomes negative. It's perfectly fine to have a negative SPL. We have some points on the graph for that. -2, -3 dB. This other dashed audiogram or hearing sensitivity curve is for a different species, the cat. And the cat hears down to about -10 dB SPL. At least this group of cats did. The cats also hear higher in frequency than humans. Dogs and cats can hear about an octave higher, that is a doubling of frequency higher than humans do. And maybe some of you have had dog whistles that you blow and you don't hear anything, but the dog comes because it's a very high frequency beyond the upper limit of human hearing, but well within the hearing range of those species. So different species have different hearing ranges.
Professor?
Yes.
Sorry, just to clarify, is a micropascal then equivalent to a decimal?
No, these are units of pressure, okay? Micronewtons per square meter, and this is a unit of pressure. SPL is just in these units called decibels, and it doesn't have a physical, it's not a pressure. It's right, it's the log of that. Any other questions? Okay, so these are sort of the lower limits of hearing. When you go into conversational levels, or the level of a lawnmower, or the level of a concert, the levels get higher, still certainly within your audibility range. As you go to higher and higher level, you risk damage to your hearing. And at that risk level, which it says high risk threshold here, right around 120 dB, sounds become painfully loud and damaging to your hearing. Okay, and that's what this shaded area refers to. Gunshots, jet aircraft engine, and we'll talk about that during our lecture of hearing loss. Okay, so I have some demonstrations because a lot of people have trouble with the decibel scale. So what is a decibel and what does it sound like when you change the sound from 50 dB to 60 dB? Well, this demonstration is 3 parts. And let me read the text first. Broadband noise, sometimes it's called white noise. Broadband noise and white noise are synonyms. And what is white light as a visual stimulus? All wavelengths, right? And so broadband noise means it has all frequencies. It has 10 hertz, 20 hertz, 30 hertz, 1,000 hertz, 2,000. It had all frequencies. And it sounds like the sh sound. Okay, so you hear the sh. It'll start out pretty loud. It'll be reduced in 10 steps of 6 decibels for each step. And I think you'll be able to very clearly hear the difference between the first and the second steps. And demonstrations are repeated once. Okay, the second demonstration is same noise is reduced in 15 steps now of 3 decibels. So there's a little bit of a smaller scale, though. You'll still be clearly audible. Third, broadband noise is reduced in 20 steps of now 1 dB. So let's listen to see if we can hear 1 dB steps.
The decibel scale. Broadband noise is reduced in 10 steps of 6 decibels. Demonstration will repeat at once.
Okay, was that clear, the difference between one and the other? So that's what 6 dB sounds like. Now, you guys who are up here close to the speakers, you might be starting at 85 dB SPL in the first one. It's pretty loud. 6 dB lower is 79, and then so on and so forth. You guys at the back are further from the speaker. You're not starting at the same level. You might be starting at 60 dB. You're still going down 6 dB to 54 dB in the next step. Everything is linear in here. It doesn't matter where you start from as long as you're going down 6 dB. So where you start doesn't really matter in these demos.
Broadband noise is reduced in 15 steps of 3 decibels.
Okay, still clear the increment between one and the other. Okay, now here's the 1 dB steps.
Broadband noise is reduced in 20 steps of 1 decibel.
Okay, so how about for that? Would you be able to stake your life on the fact that you could tell one from another? No, I see a lot of heads shaking. Okay, well, if you sit there and do this over and over again and really train yourself, apparently 1 dB is the just noticeable difference that most observers can hear. So 1 dB is the just noticeable difference in SPL. Okay? Okay? So how do we do that? Well, you have an auditory nerve, and at 60 dB, your auditory nerve fibers are sending this many spikes to the brain. At 61 dB, they're sending maybe a few more spikes, something like that. It's not absolutely clear how you do that. There is more information coming in from the ear to the brain as a function of sound level. We'll talk a lot about that. Now, we also talked about sound frequency. Okay, JND for sound level is about 1 dB. What is it for sound frequency? Well, we're going to have pretty much a whole lecture on that. But your ear is extremely good at telling one frequency from another. So if you start at 1,000 hertz and change it to 1,002 hertz, a very, very small change, you can tell the difference. Your ear is a fantastic frequency analyzer. So we're going to have a whole lecture on exactly how your ear does that. But the JND for sound frequency is also a good demonstration. We'll play that when we talk about sound frequency coding. Okay, any questions about that so far? Okay, let's switch back to the physical characteristics of sound. And these are some very common auditory stimuli. We've heard a noise just now. And if you graph the sound pressure as a function of time, this is what the waveform looks like. Okay, how could you do that? You take a microphone, stick it out in front of a noise source, and run that into an oscilloscope. The microphone converts the sound pressure into a voltage. The oscilloscope displays the voltage signal as a function of time. You can look at that. Auditory scientists like to look at things as a function of time, of course. They also like to look at things as a function of sound frequency. Okay? This is a graph for this same stimulus, the noise stimulus, now as a function of frequency. And we said before, the noise is broadband, it's white noise, it has all frequencies. And here is the graph to show you that. This might be the energy, and this is as a function of frequency. So it has all frequencies. It's trailing off a little at the very highest. That may be because the microphone couldn't wiggle back and forth at very, very high frequencies. But it's essentially a flat frequency curve. And sometimes this display is called the spectrum. Okay, so spectrum or spectra are graphs as a function of frequency. Sometimes people talk about this as the frequency domain and the time domain. If you've taken any electrical engineering courses here at MIT, people will talk about the time and frequency domains. And how can you go from one representation to another? Well, you can take your microphone signal, instead of going to the oscilloscope, going to the spectrum analyzer, which is a machine that can give you this nice plot. But how about mathematically? How can you do that? The Fourier transform, right. So of course, Fourier was a mathematician who studied various things, heat transfer and other things. He developed this transformation. If you have the mathematical description of a time varying signal, you can plug it through his equation, the Fourier transform, and come out with the frequency representation or the frequency domain. Or vice versa, if you have the frequency domain, you can inverse Fourier transform and go back to the time domain. Okay, we're not going to talk too much about transforms here, but it is interesting because, as it turns out, the ear, your inner ear, is a wonderful frequency analyzer. It can tell the difference between 1,000 and 1,002 hertz. This is a very nice way in the ear of detecting the different frequencies. And so these time and frequency domain representations are very convenient for us to look at. So just keep that in mind. Here's a very common auditory stimulus, the pure tone or the sinusoid, right? This is the sinusoidal waveform in the time domain. In the frequency domain, it only has one frequency, the frequency at which that thing is going back and forth in terms of hertz. And this is a hertz axis, right? So sometimes it's called a pure tone. Why is it so pure? Does it have high morals or what? No, it just has one sound frequency, okay? These other stimuli, we're going to listen to this in just a minute. This is a so-called square wave. And imagine trying to add up a whole bunch of pure tones to result in a square wave. It seems impossible, right? Well, it's possible if you use an infinite number of frequencies, and this frequency representation for a square wave goes on basically forever, right? To get those corners of the square wave sharp, like a true square wave is, you need lots of individual frequencies, lots of pure tones, if you will. Okay? Tone bursts are some common auditory stimuli. We'll talk about those later in the course. Click is a very common auditory stimulus, so it's a sound like this. Or last night, it was the sound of a fastball hitting a wooden baseball bat, right? It's a very sharp, impulsive sound. Very nice sound if you're behind the team who's batting. So a click, that baseball hitting the bat, doesn't happen for very long. A click can be infinitesimally short, right? the time that the baseball is in contact with the bat is pretty short. And if it's very short in the time domain, then you have all frequencies. So it's another example of a broad band or broad spectrum sound. If the click is infinitesimally short, the spectrum is completely flat. Okay, so those are some common auditory stimuli. And let's go through some more complicated and maybe more interesting sounds. Okay, well, all of us like to listen to music, right? So here are some examples of musical sounds. This is a piano keyboard, and here is the spectrum or frequency representation of what you get when you strike one key on the piano keyboard. So that's one note, right? Well, sure, it sounds like one thing, but you have a whole bunch of different frequencies that go along with it. And why is that true? Does anybody know? Why do you get a whole bunch of different frequencies when you strike a key on the piano keyboard? Yeah?
Isn't it vibrating all along the length? So there's different like wavelengths.
What's vibrating
It's
in
not
piano?
just like an infinitely small portion of the string. It's the longer string has parts that are shorter still vibrating all along the length.
Yeah, you're getting there. So in the piano, the string is fixed at one end, and it's a long string. It fits on the other, and your key that you press down makes a hammer go up, and there's a bunch of linkages. And eventually the hammer hits that string somewhere. And the string, it's fixed here. It's not going to move. It's fixed here. It's not going to move. But in between those points, it can move. And so it can vibrate like this. Right? It can go up and down. It can also vibrate like this. You can have what's called a node in the middle. Right? In fact, if you put your finger right here and fix that middle, it wouldn't allow the string to vibrate in this uniform fashion, but it would allow this half to vibrate and that half to vibrate, right? This node is sort of a constraint for the string, right? It can also vibrate like this. Wish I had a different color. Over here? Ah, great. Okay, you can also have this string vibrate like this, right? Okay. Now, and it can vibrate in many, many different patterns, right? I've just drawn a few. What's interesting is that this length is twice as long as this length, which is twice as long as this length. And what would you expect the time of those vibrations to be? Well, the big long thing is going to vibrate pretty slowly, right? That's what's called the fundamental frequency. The thing that's vibrating in two parts, it's shorter and it can vibrate faster, right? In fact, it vibrates twice as fast. So the first harmonic is twice the frequency of the fundamental. And so on and so forth. You can get from the physical characteristics of the vibration of that string a whole bunch of different vibration patterns. And they're usually a harmonic series, twice, 3 times, 4 times, 5 times, 6 times, the fundamental. Just because of the physical characteristics of vibration of the string. And the wind column in the case of an alto saxophone. Okay? When you hear that one note hit by the hammer, all of these vibrations are happening at once. And so that one sound sounds like one thing. Musicians would say it sounds like a note, A above C. Okay, but you have a whole bunch of different harmonics in it. What is pitch? Okay, pitch is of very interest to people who study the auditory system, to musicians. Pitch is that attribute of the sensation, auditory sensation, in terms of which sounds can be ordered on a musical scale. Okay, let's say I didn't let you see the keyboard, but I recorded the sounds and I pressed some sounds down there, some in the middle, some way up here, some way at the high end. And I gave you 20 different recordings. And I said, well, make a ranking of them. Put these down low, those are number 1 and 2. Put these in the middle, those are number 10. And then up to the high end, the highest one is 20. You could do that. The ones that were down low would be called those with low pitch. The pitch of a pure tone, of course, depends on the frequency. That's as if you were just giving 1. If you move that around up high in frequency, it sounds like a really shrilly, high-pitched sound. If you moved it down low, it sounded like a real low sound. The pitch of a complicated sound, that is with many overtones and harmonics, depends strongly on the fundamental frequency. But sometimes the fundamental, for example, in this guitar sound is pretty weak. And in some cases, you can take it out altogether. The pitch doesn't change that much, surprisingly. So somehow the ear knows by this pattern of spectrum that there should be a fundamental there, and it can stick it back in. So that's what pitch is. Another sensation that musicians often talk about is the timbre of a sound. And the timbre is sort of the quality or the identification of a sound. And it relates to the highest harmonics here and the pattern of this harmonics. For the piano, it's starting big and sloping down. For a guitar, it's starting small, sloping up, and then sloping down. The timbre is what allows you to identify that sound that you heard as a piano. We can all hear a piano and say, yeah, that's a piano. We can all hear a guitar, that's a guitar. Or that's an electric guitar because its pattern of harmonics, its fundamental harmonics, differs. That's how we identify sounds, is by their timbre, or their spectrum, if you will. Okay, so those are pretty complicated sounds. And what do I have next? Yeah, I have a demonstration. This one is called canceled harmonics. And it's a very nice demonstration to illustrate the idea that I said, well, when you have all these harmonics go on together, it sounds like one thing, one note, one sound. But if you take some of the harmonics out and put them back in, you're aware of that taking out and putting back in. So what they're going to do is give you a complex tone is presented, followed by several cancellations and restorations of a particular harmonic. And let me show you what complex tone they're going to give you. It's simply this square wave. This is what you're going to be listening to. It sounds like eh. It's not very musical at all. And it has a fundamental and a whole bunch of harmonics, an infinite number. When that complex goes on at once, you're going to say, that sounds like a nasty sound. It sounds like a buzz almost. Then they're going to take this one harmonic and pull it out. And then they're going to put it back in. As they do that, you're going to say, well, that sounded differently. When it was out and when it was back in, I could hear that thing going in and out. And then they're going to do that for the second, third, and fourth, on up to, I think, about 10 or so. Even though this whole constellation sounds like one sound, when they pulse these things in and out, you can tell. Okay, let's listen to the demonstration. And let's see how many times they're going to do it. This is done for harmonics 1 through 10.
Canceled harmonics. A complex tone is presented, followed by several cancellations and restorations of a particular harmonic. This is done for harmonics 1 through 10.
Okay, could everybody hear when this complex went on all at once? It sounded like one sound. And when individual components were taken out and pulsed back in, you could identify them. Your ear is very good at distinguishing the various frequencies in a complex spectrum. All that message is sent to the brain as individual channels, and the brain somehow perceives that when everything is going on at the same time, that's one sound. It's really not of interest to the brain that the string is vibrating a whole bunch of different frequencies. It's that there's one string vibrating, okay? But if you took out one of these modes, in other words, if I put my finger here and the fundamental goes away, your ear is very good at detecting that, and it sends a message to the brain that the fundamental is no longer there, and the brain says, something different has happened. Okay, so the ear is very good at recognizing those different characteristics. The brain is good at putting them back together and say they started at one time, so it's one object. Okay, questions about that so far? Now, the last type of complex sound that I want to cover is speech sounds. And I want to save most of this for the end of the semester when we talk about the parts of the auditory system that are active in distinguishing different speech sounds. But let me just, because we're talking about sounds and complex sounds, talk about speech sounds. So this is a diagram of your vocal cavity. Way down at the bottom here, you get air from your lungs that goes through your trachea, and in the trachea there's these vocal cords, if you will, that are scientifically called the glottis. Okay, the opening in between is the glottis. Okay, so air can come out, or if you use muscles associated with your vocal cords, you can close that off. Okay, now as the air comes out from here, it moves those vocal cords back and forth, and they hit each other and they open up, and they hit each other and open up. And as they do that, they interrupt the airflow and they allow it to pass through, and they interrupt it, they allow it to pass through. And if you were to put a microphone way down your trachea, right above those vocal cords, you would see this time waveform. The pressure would go up right as the air pressure is coming from the lungs when the vocal cords were open. When the vocal cords are shut, there's no pressure there, right? Or it's just atmospheric pressure. So this opening and closing of the air through the glottis forms this very complicated waveform. If you look at the spectrum of it, it has a whole bunch of different frequencies. The lowest of the frequency is the frequency that these things are opening and closing. But there's a whole bunch of harmonics. So it's a very complicated spectrum. The upper part of your vocal tract is what's called a filter. And it serves to emphasize some of those harmonics and de-emphasize others. And the filter function is indicated here having 3 peaks. Those peaks are called formant peaks. Okay? And they have to do with the shape and dimensions, lengths and widths of your upper vocal tract. And what's kind of neat is by manipulating, like let's say where your palate is and where your lips are and where your tongue is, you can change that filter function by using the muscles that move things around in your upper vocal tract. And after you filter this complex spectrum, you come out with a function where some of these spectral peaks are emphasized and some are not emphasized. And here's the function that you would get right outside in the air outside the front of your mouth. This is the time waveform here. Okay? Now, here are some examples of manipulation of your upper vocal tract. For instance, here the lower part of the mouth is moved way up high, and it produces an acoustic spectrum where you have a big F1, And F2 and F3 are small, and they're way up high in frequency. And contrast this with when the bottom of your mouth is lowered and moved backward. Here, F1 is even lower, F2 is quite low, and F3 is moderately low. And these are, of course, the way you pronounce different vowels. So we can all say these two vowels. This is the vowel I, as in hit. So just everybody say that, hit, hit. And you can kind of feel that the lower part of your mouth, the lower part of your mouth is moved upward. Whereas if you do something like this, like ah and call, call. Everybody say that, call. You can feel the lower part of your mouth dropping down, as indicated here, and making a big cavity. Whereas here, the cavity is very small. Changes the acoustic spectrum. Our ears pick it up. And our ears are very good frequency analyzers, and they say the spectrum here sounds like hit, because you've learned to associate that spectrum with that vowel. This is a different spectrum. Our ears pick it up, and they say, oh, that's the vowel ah, as in call. Okay, so that's how speech sounds are formed. At least this works very well for vowel sounds. It doesn't explain things like consonant sounds, which, of course, there are many different kinds. There are stop consonants where your lips close down before you utter the consonant p. So p, everybody close their lips down, and then all of a sudden you open it up. It's a completely different thing. That's not modulating the spectrum. That's modulating the time pattern. These vowels are distinguished by their different spectral patterns, which is picked up by your ears. So I just thought you'd want to know about that. Speech sounds are among the most complicated acoustical sounds because of the number of frequencies involved, the formation, and of course the perception of, telling, for example, one vowel from another. Okay, so let's shift gears and move on. Instead of talking about the physical characteristics of sound, let's talk about how we hear sounds. And we're only going to get as far as the auditory periphery today, but let's just define it. The auditory periphery is this whole structure indicated here, and it's usually separated into three parts: the external ear, the middle ear, and then the inner ear. Those are the three very big divisions of the auditory periphery. In the external ear, you have your pinna. Okay, here's your pinna. You have the ear canal, which goes down about 3 centimeters inside your head. And it ends up at this yellow structure here called the eardrum, or tympanic membrane is its scientific term for the eardrum. That's the end of the external ear. The middle ear is an air-filled cavity. So we're still talking about sound and air. And in that middle ear cavity are 3 small bones. They're called ossicles. I think, here we go. And in high school biology, you probably learned them as hammer, anvil, and stirrup. But the scientific names are the malleus, incus, and stapes. Okay, and they convey the sound vibrations of the eardrum. When sound hits the eardrum, it causes it to move. And these bones are linked right onto the eardrum, and they're linked one to another. The eardrum then moves the bones, and the bones finally end up, in the case of the stapes, in the inner ear. So that's where the inner ear begins. So I have a demonstration of ossicles, and I'll pass them around. These are ossicles from a guinea pig, and they're glued to the bottom of this little vial. And I made a kind of a crummy drawing of them. But if you hold this vial so that the piece of tape on it is downward, you get this view here. You have the stapes. And I didn't list the other ones. But in the guinea pig, the incus and malleus are fused, so they can be considered one. This is definitely part of the malleus, but I don't know where the incus ends up and the malleus begins. And if you had an eardrum, it would be this dashed line here. Okay, so let me just pass these around.
Thank you.
And you can probably appreciate from my diagram how the high school biology name for the stapes got its name. It's the stirrup, right? What's the stirrup? Does anybody know what a stirrup is? Yeah, when you ride horses, what is the... You put your foot in it, right? And that's why cowboy boots have a nice big heel, so your foot doesn't go all the way through it, and it sticks in your heel, right? And so this is the stirrup. You put your cowboy boot right in there until your heel hits this foot plate. Right? So that's pretty obvious how that got its name. It's the foot plate where you put your foot. Your foot goes right on that. And that foot plate is the beginning of the next division, which is the inner ear. Okay? And by the way, I should point out before I forget that what is the smallest bone in the body? All answers are given. Okay, the stapes is the smallest bone in the body. Why? Well, it's got to move. And lousy little sound makes this tiny little eardrum. Remember, the eardrum is basically a tiny little thin piece of skin, right? It's like saran wrap. When your doctor looks down your ear canal, that doctor can look right through the eardrum. It's so thin. It's like plastic wrap. And the doctor can look into the middle ear and say, oh, there's so much fluid in there. You got a middle ear infection. Or they can say, oh, middle ear looks good. You got some other problem, okay? That's what they're looking at. They're looking with their otoscope and a light right through the eardrum into the middle ear. And that whole middle ear, eardrum and the ossicles have to vibrate when there's a tiny little sound like a pin drop. Okay, the pin drops right there, and you can hear it because these things are so light and flexible that they can vibrate, and so small. Okay, the stapes foot plate ends up at the cochlea, and the cochlea is the main part of the inner ear. And cochlea, as it says here, gets its name from the Greek word cochleus, which means snail. And certainly the inner ear looks like a snail shell. And in the inner ear, here's where sound changes from sound in air or maybe sound in the bones. The inner ear is filled with fluid. Okay? And inside the inner ear are these wonderful receptor cells for hearing and the beginning of the auditory nerve. Here's the auditory nerve that's sending messages centrally into the brain. So the brain would be beginning right here. This whole structure here, all this gray stuff, and even the shell of the cochlea is bone. And it's your temporal bone, right? The temporal bone is the hardest bone in the body, right? You can have a severe blow to the head, and that temporal bone will keep all these structures intact. It's very, very hard bone. And surgeons at our hospital do a lot of drilling with the dental drill to get down to these important structures if they have to manipulate them. These loops here are part of the inner ear, but they're a part that is sensitive to vestibular sensation. So those loops are called the semicircular canals. They're almost circular, and they're in the three planes, X, Y, and Z. And when you rotate your head, let's say side to side, one of those canals can move, and the receptor cells in it can sense that movement and detect that your head had moved. And it's very important because if you want to keep your eyes fixated on one point but move your head, you can do that by the vestibulo-ocular reflex. So the neurons from this vestibular system send messages into the brainstem, and eventually they go through coordinating centers into the motor neurons for the extraocular muscles, which can, of course, move your eyes when you want to do a saccade or pursuit, or they can keep your eyes stabilized, which is moving them with respect to your head, even though your head's moving. Okay, but we're not going to talk about those. Okay, now let's talk about the function of the middle ear and the external ear. That's what we're going to talk about for the rest of today. Oh, I have a model. Let me just pass around this model. I think we passed it around before, first day of class, but you can look at it again because we're going into more detail today on these structures. So this comes apart. So here's your pinna. Here's the long ear canal. Here's the eardrum. And if I tilt this here, you can see the structures we're talking about in the inner ear, the cochlea, the semicircular canals, and this yellow structure here is the auditory nerve. This is then going into the brain. The brain's cut off here. This is the eustachian tube, which is a way to vent the air-filled middle ear. Okay, so you want to purge that with air. If you go up hiking in a tall mountain, the barometric pressure outside gets lower. You want to equalize that in your middle ear. You open that eustachian tube, usually by swallowing. The ossicles are here, and if you take out this inner ear, the stapes is fixed with it, so you can see the stapes. In terms of size, this whole inner ear, the cochlea, is about the size of an aspirin tablet in a human. So it's about that size. Okay, let's pass that around. Okay, what is the function of the middle ear? Why do we have these three bones? Why do I have the eardrum? Why doesn't sound come right in and strike the inner ear itself? Well, it turns out that if you look at the physical characteristics of sound in air, and you want to get that airborne sound to sound in water, different medium. So this is fluid or water. This is air. Sound's coming in here, and you want to get it into the fluid of the inner ear, which is essentially water. That if you don't do anything and you have the sound coming in here, most of it bounces back off. In fact, 99.5% of the energy of sound in air at a fluid boundary is reflected back into the air. So if you're in a boat here, I didn't draw this right, you're in a boat here, you're fishing, you're talking to your buddy in the back of the boat, and you say, "Pass me another beer," and your buddy says, "Be quiet, you'll scare the fish." Actually, the fish can't hear you because most of the energy in your saying, "Pass me a beer," bounced right back off into the air. Okay? So how does the auditory system deal with this? We want to listen very carefully to a pin drop, but most of the energy bounces back off at this boundary between air and fluid. Okay? That's the job of the middle ear. Okay, so here is how the middle ear moves. This is a nice movie made by Heidi Nakajima at Mass Eye and Ear Infirmary. So the orientation is a little bit different, but this is the eardrum. This is the malleus, the incus, and the stapes. Together, they're the middle ear. I said this inner ear is the cochlea here, and it's encased in bone, fluid encased in bone. So how does this stapes work? Well, there's a little window in the bone. It's called the oval window. And the footplate of the stapes pushes on that oval window. It's not indicated here, but it's right underneath this oval part. There's another window called the round window. That's indicated by blue there. And it's just a pressure relief point, because if you pushed on fluid, it would push back to you. Fluid's relatively incompressible. And so this pushing in means this membrane over the round window can push out easily. So it's easy to push in and pull back because this membrane can give. As you can see, the sound, motion of these bones is coming into the fluid quite nicely and changing some membranes inside the inner ear. The job of the middle ear is so that most of that sound energy gets into the fluids of the water of the inner ear. And how does it do that? The primary way is by changing area. The eardrum is this big drum, okay? And the stapes footplate is this much lower in area or smaller structure. Okay, and there's some formulas here. P1, A1, those pressure and area at the tympanic membrane, equals P2, A2, where there's the same characteristics at the stapes footplate. And so when you decrease the area a lot, where A2 goes way down, P2 has to go way up. And so that's the main way that the middle ear allows sound and air to go into sound and fluid. The engineers would call this impedance matching. And they would say that when you change media, the impedance of one medium being different from another means that most of the energy is going to bounce back off. If you have a device here, like the middle ear, to make the impedances more matching, much of this energy is going to then go through the boundary from one medium to the other if you match the impedances. And one way of matching the impedances is to change the areas. Another way, and this may be the reason we have 3 and not just 1 middle ear bone, is by a lever action. Okay, so this is kind of like a lever. Well, the fulcrum is off to one side, not right in the middle. And you can obviously get force amplification from a lever action. A third mechanism might be a buckling of the tympanic membrane. And you'll have to read. I'm not an expert on that at all. I'm not even sure if that's in vogue these days. But these actions are much less than the change in area offered by the eardrum. So what happens when a patient comes into the Massachusetts Eye and Ear Infirmary and for some reason, either via an accident or a developmental problem, they don't have an eardrum and they don't have these 3 ossicles, so that the sound goes right in from the outside and strikes, let's say, the round window of the cochlea. Are they deaf? Well, no, they have a hearing loss. Some of the energy gets through into the fluid. How big is their hearing loss? Well, this is the so-called audiogram that's generated when you visit a hospital and you complain that your hearing isn't so good. They send you down to the audiology department. They put you in a testing booth. They put your earphones on, and the The tester goes outside so they don't make any extraneous noise. And they say, raise your hand when you can hear the sound, when you hear a sound. So they test your hearing, and this is a so-called audiogram. And plotted on the y-axis is the amount of hearing loss in decibels. That's just the way they plot it. And plotted on the x-axis is the frequency. And they typically test 250, 500, 1,000, which is abbreviated here, 1K, 2K, and 4K. They typically don't test the extremes of the human hearing. They test the middle range. And this is the range over which most speech sounds are made. And that's the most important for most people. When they say, I can't hear very well, it means they can't understand somebody when they're speaking. And this is the audiogram from someone who lacked a middle ear. And this 40 dB here, across all the different frequencies, approximately 40 dB, is the amount of hearing loss they have. Okay, so if you go back to the audiogram that we had in the first slide of today's lecture, everything would be lifted up by 40 dB. You have a 40 dB hearing loss. You're not deaf at all, but that's a moderate to severe hearing loss, a 40 dB hearing loss. You might have problems. You certainly would have problems hearing a pin drop. You might have problems hearing a telephone ring if it were on the other side of the room. Okay? You might have problems with conversation. A treatment to that would be several types of treatment. The surgeons in the ear, nose, and throat department at Mass Eye and Ear could reconstruct your middle ear and your eardrum. They could use a skin flap, a piece of skin taken from somewhere else on your body, put in the place of the eardrum, and they could use some either wire or Teflon or plastic pieces that could connect that eardrum into the oval window of the cochlea, so they can reconstruct the middle ear fairly easily. If the person doesn't want to have surgery, they can have a hearing aid. Essentially, you have a flat frequency loss here, so put a device in the ear canal that boosts every single frequency by 40 dB. Amplify the sound. So a hearing aid works pretty well for these people with this type of a hearing loss. This type of a hearing loss is called a conductive hearing loss because it's in the conductive mechanism to conduct the sound from outside your body into inside your body. It's a conductive hearing loss. So that is the job of the middle ear, to ensure efficient transmission of sound and air into the fluids of your body. And without it, you have a moderate to severe hearing loss. There's a disease called otosclerosis. Oto meaning hearing, right? My department at Harvard Med School is otology and laryngology. Otology and laryngology, right? And sclerosis means hardening or rocky or bony growths. Okay, and the surgery that happens sometimes around the stapes, bony growths can grow around it and fix the foot plate so that it can't vibrate anymore. So what's done for that is you take out the stapes, you take off the bony growths, and if you just put the stapes back in, often these bony growths grow again. So actually you take it out and replace it with an artificial stapes. And the operation is called a stapedectomy. Right? The stapes, and ectomy means taking it out. You replace it with a prosthesis. It's a very successful surgery for otosclerosis, which is a conductive hearing loss. Okay, so that's the job of the middle ear, and that's relatively easy to treat when there's a problem. What is, or is there, a function of the external ear? Okay, well, a lot of textbooks say the external ear funnels the sound into your ear canal, okay. But there is another function of the external ear that's more on the lines of localizing sounds using your external ear. Okay, and these are examples of external ears, or pinna, in different people, and everybody has a slightly different one, right? Who is this historical figure? Anybody? He was a president of the United States, LBJ, right? President Johnson. He was always caricaturized by the political cartoon guys with these huge ears, right? Big pinning. But everybody has different shaped pinning, okay? It turns out that the external ear can help you localize where sound is coming from. Okay, well, how can it do that? Well, if you have a pinna and you do this interesting experiment, you take a microphone, and put the microphone inside. Here's the pinna. Here's the ear canal. Put the microphone out here and start out with a completely flat spectrum, broadband noise. The noise is absolutely flat so that it has equal energy at all the frequencies. Okay, you measure it out there, and then you move your microphone down here in the ear canal, maybe near the eardrum, and measure the spectrum again. And so this is plotted in terms of gain with respect to free field. Free field is out here. Okay, free field means basically in the room or in the environment. And now we're going to measure the spectrum down here and plot the gain. So anything above 0 is going to be higher than in the ear, and everything below 0 is going to be lower. And let's look at this solid curve here, which is minus 15 degrees elevation. So elevation of a sound source, if it's straight ahead, it's 0. If it's minus 15, it's 15 degrees below 0. If it's above 0, it could be 15 degrees. Well, in this case, it's 7.5 and 30. So elevations that are positive are above you. As that sound source moves around from being below you to above you, its spectrum changes. The spectrum way down here at the eardrum. And in particular, so there's some very sharp dips or nulls in the spectrum that move around. It's thought that you can use those nulls as a cue to where this sound is. Now, what causes those nulls? Well, because the pinna is very complicated, you can imagine that some sound comes in and strikes the pinna and reflects off it. And maybe it reflects, excuse my artistic abilities here, maybe it reflects into the ear canal. Contrast that with other sound that comes straight in. Eventually, these two sounds are going to meet up at a point. And let's say this sound, taking a longer time path, went through half of its cycle. So that now, this sound, when it's starting to go in negative pressure, meets up with this sound, which came straight in and is starting to go in a positive pressure. Okay, positive plus negative could sum to 0. And the geometry has to be just right, and the frequency has to be just right. But it can be just right at a particular frequency, and that's what causes the nulls. It's just a physical characteristic of two sound sources meeting up. It is thought, then, that you can learn the position of those nulls, especially, to be associated with positions of sound in space. And that's what was done in the research report for today. These are some data from 4 different subjects. They tested the subject to localize sounds coming from in front of them. Left and right would be azimuth. That's plotted on the x-axis. Up and down would be elevation. That's plotted on the y-axis. And they moved the sounds around in different places. And they said to the person, tell me where the sound is coming from. The answers that the subjects gave are in these solid, thick lines. The real positions were on the thinner lines. And the individual data points are the small points, and the average data points from the subject are the big points here. So these subjects, when given a checkerboard of locations, they could pretty faithfully tell the investigators where a sound was coming from, both in elevation and in azimuth. Okay, these are data from 4 different subjects. What was done in the experiment is distort the pinna. How are we going to do it? Well, we could move our ear a little bit. What they did was they put in a little clay mold in parts of the pinna to change the shape, and they did that on both sides. As soon as they did that, these are now the answers from the subjects. Terrible in terms of elevation sensitivity, determining where a sound is coming from in terms of different elevations. Still pretty good in azimuth. There are other cues for sound azimuth that involve using 2 ears, which we're going to talk about extensively later this semester. The elevational localization was completely disrupted when the pinna shape was disrupted. Have these subjects go out for a few weeks, come back, get tested again. They relearned with the pinna molds in how to localize sounds. Okay, this is an example of relearning or plasticity. And now the pinna cues had different nulls because the pinnas were shaped differently. They could relearn these new cues and associate them with the same old changes in elevation that we had before. So that's why it's called relearning sound localization with new ears, or new or distorted ears. So this is an example then of subjects learning to associate these new cues with the old sound localization positions. So that's the take-home message from this research report by Hoffman et al. Okay, questions? All right, if not, I'll see you again on Wednesday, and we'll talk about the inner ear.